Oh, wow, the recording worked on the first try. This has never happened before. That's a good omen, I'm sure. Well, I think we can start. Welcome back, everyone. You can definitely tell we got through midterms week. We have about half the class here, so good on you for your work ethic and making it here after our tough midterms and getting through the second exam. I think we practically deserve a break. And that's just what we're going to get. We finished chapter 5. That's probably the hardest chapter of the course. And now we're going to start working on normal distributions and finally our inferential statistics in chapters 8, 9, 10, and 12. Well, any questions at all, folks, before we get started with our work today? Okay, as far as the exam 2, I should have this graded and returned. I'm hoping on Wednesday, but it'll be on Thursday at the very latest if I am still a little bit behind. So I'm struggling to catch up, but we're nearly there and all caught up. But for the moment, we're in section 6.5. And the good news about section 6.5 is, it starts off as a pretty light topic and it's really not too bad. The reason for that is we've seen this information already, quite a bit of it. Let's jump in and take a look. So I can clear these drawings, there we go. So here's how the section starts. We're really talking about the normal distributions, and when we say that, that's no different than the empirical rule. The empirical rule told us if we draw this curve, which we sometimes call the normal model or the normal distribution or the normal curve, it comes up with this mound-shaped or bell-shaped curve, which is nicely and symmetric. And we have approximate values of just where to find certain areas of these regions. For example, 34% of the area is right where the red dot is, between this dashed line for the mean and this dashed line where we're 1 standard deviation to the right. So our goal is to work with this a little bit more and see just what kind of interesting things we can do with it as far as probabilities go. And speaking of probabilities, that's kind of the weird thing about covering this all the way back in section 3.5. We needed it because we need to describe what is the standard deviation really doing as far as telling us how spread out the data is. But now, when we see all these percentages, we can think of them as probabilities. 34% you can think of as a 0.34. And here's the idea with this new probability model we're working on. We think of this horizontal axis as an x-axis, just like if we were dealing with a dot plot or a box plot and so on. So this will be x going this way. And now we can ask questions about x relative to probabilities. For example, here's one question you could ask about it. Probability that I'll put x in the middle. And let's say it's between -1 standard deviation and +2 standard deviations. Let me see if I can format that a little bit better just to make it fit. So -1 standard deviation. SD standing for the standard deviation we see written here. So I want that to be less than x and x less than 2 SD for standard deviations. So we can now calculate this as a probability, but we've really done it before. Here's the way it really works. Whatever this comes out as, it's going to be equal to, actually I like that pen, let's stick with light blue. This is going to be equal to the area under the curve between -1 SD and +2 SDs for standard deviations. So now with this probability model, if we don't have counts, we're doing hypothetical tables. If instead we put a continuous smooth curve like this, probabilities are now areas. So that's our big change of point of view for this section right here in 6.5. Any questions about that so far? And I notice that's not completely too readable. Let me see if I can dim the lights just a little bit to improve that. And if that doesn't improve it, I'll just not use that color again. Is that a little bit better for folks on reading that? Okay. So that's what our probabilities are going to turn into. And now we can answer this question right here as well. This is going to be equal to, we need to start from -1 standard deviation. So right here, we're going to go from here all the way out to +2 standard deviations. So we stop right here. And we need to take all of this area under the curve. Now that's kind of a weird question because we see percentages, right? But we want areas. So here's one of the very bizarre facts about the normal distribution. The total area under this curve, by this curve, we mean the black line got overwritten as blue right around this region. But the total area is exactly 1. It's kind of a surprise in a certain sense, and we'll see some reasons why that is a very surprising mathematical fact about this curve. If it has an area of exactly 1, then we can just take the percentages that we have highlighted here, convert them to decimals, add them up, and that is the exact correct area. So the work turns into now this. I'm going to take these 3 right here. So it's going to be 0.34 plus 0.34 plus 0.135. And this is going to become, let's see, that's going to be 68.68 plus 0.135 should be oh, that's addition with carry. You know what? A calculator is probably a good call on this. Let's treat ourselves to a slightly easier computation. It'll be 0.68 plus 0.135, giving us a value of 0.815. So the probability that whatever x might represent, it might be height, it might be time, but if it's between -1 standard deviation and +2 standard deviations, we're expecting this in probability, 0.185. All we're doing is grabbing the area under that normal curve. Definitely a new point of view, but in a certain sense, not all too different than how we computed before. We just have some kind of organization here. It could be a table, it could be a two-way table, a chart, or a diagram like this one. Grab the right values, add them up, and we have our probability. Any questions at all, folks, with getting that computation there? Okay, now here's the unfortunate fact about this probability. I wrote equals everywhere, and that's okay. It's understood that we're approximating. But if we want to be really, really honest with that answer, maybe the best thing to have done is write approximately equals right here. This is a reminder, because all of these percentages were just rough approximations. That's not fair. They're not rough. They're pretty accurate. If you're rounding to say 1 decimal spot right here, these are not too bad as approximations. We want to do a better job. We want to calculate these exactly, or at least exactly up to a certain level of decimal places. And so that's why we have to change gears and just talk about normal distributions. They all look like this, but we're not going to use the empirical rule going forward because the empirical rule is just too restrictive. You have to have exactly -1 standard deviation, not say -1.5. That's out of the question for this. And even if it's lined up perfectly with the standard deviations, like we saw here to here, it's still just an approximation. So now, here's what we're going to do instead. We're going to define the normal distribution as a true mathematical object and give it an actual formula to plot. This is not a formula you have to memorize. Let's mention that right here. It's really just here for the sake of completeness, so you know what we're talking about when we say normal distribution. This weird formula is the equation for this curve that was sketched right up here. So let's say, just as a reminder, not necessary to memorize. It's here for us so that we can start working with the normal distributions and see what they look like if we were to attempt to sketch them out. We've sketched them before, but now we're trying to plot them exactly using the formula right here. So let's read through this. It says, The normal distribution is a curve that is uniform and symmetric. We know that. It's also bell-shaped or mound-shaped, as our author calls it. It is defined in terms of parameters, mu, which is the population mean. And where it says the word parameters, recall parameters is synonymous with population characteristic. Let's say that right here just for a reminder. Parameter is the same as saying population. I'll use pop for population. Characteristic. So we have a population mean, mu. We have a population standard deviation, sigma. And the density curve, the actual mound-shaped curve itself, comes in this way. This is the formula for it. Let's zoom in just a touch so we can actually take a look at that thing. So when we go to put this into any kind of plotting device, we put the mean right in this location here. The standard deviation goes into this spot and this spot. There's also a bunch of weird other nonsense going on here. There's square roots, there's pi, there's a symbol e. That's really a number, Euler's number, about 2.71. But if we put all this into a graphing device, here's what it would look like. In Desmos, here's the same plot where I put S as 1, M as 1. And it doesn't look too inspiring, right? My plot looks sad. It should look like this right here. So this is kind of the challenge sometimes of drawing these by hand. It's hard to say, well, what should it even look like? Let's come back down here and see if we can fix this. So I'm doing the first plot where mu is going to be 0. I don't know how to put Greek inside this, so I put m for mu on the notes. Now it's at 0. So S is going to take the value of sigma right here. It's going to be at 1. And the only thing we really need to correct is, well, maybe a couple things. We just need to zoom in just right. Now it's going to -5, -10. That's way too many standard deviations. Really interesting information is around -3 standard deviations and up to +3 standard deviations. So let's start making it around that location. How about -4, one extra one for good measure, up to +4. That's our curve there. Still looks pretty terrible. But now we can zoom in the vertical direction. You'll notice that whenever we dealt with the normal distribution, the empirical rule, we never, ever actually plotted this axis. That's a little bit weird. But for the sake of getting a good plot, we do have to deal with it. Let's go from, say, -1. 2 is still too high, so maybe +1 is probably better. Oh, I'm in the wrong spot. Let me try this again. +1. Finally, that's our curve. That's the normal curve that we've been attempting to plot every time it came up. And yeah, it looks totally symmetric. It's mound-shaped, and it has this nice, gentle, sloping curvature that we see here. I always mention every time we plotted this curve will never even touch the x-axis. That looks shady right here, right? But if you wanted to, you can go way out here, maybe not too far, but let's go right here. I zoom in on this location for a long enough amount of time, eventually you're going to see a separation of the curve and that horizontal axis. It truly never actually even touches it. Again, that is kind of bonkers about this, because what we're saying here is we have a curve that really goes forever towards the left. We just plot it typically around, say, -4 deviations to +4 deviations. Better fix the y-axis again. Oh, geez, I definitely don't want to log in. This goes from -1 to 1. So we have a curve that's going to the left forever. It's never actually stopping. It's also going to the right forever, never, ever, ever stopping. It will never even touch the x-axis. And somehow, some way, the total area under this curve must be exactly 1. Just trying to get this pen to work. So the area under this curve is exactly 1. That's good news for us, because if we're dealing with a probability model, we have to find a way to say the probability of everything comes out as 1. This time the sample space is the entire real number line. Going that way, -4 is in the sample space, but so is -4 million. Goes that way forever. And so if we look at the entire area under the curve, we're really using this formula. The probability of the entire sample space must be exactly 1. A very, very bizarre object altogether. Do you folks believe it, that the area could be 1? Honestly, when I first saw this, I had my doubts because the rationale here is if the area is really actually 1, and you're allowed to go left forever, and there's always a gap between the axis and the curve, you're always getting area to the left. Every time you move towards the left, you're adding more and more area. The magical thing about this curve, the reason it really does work out with total area exactly at 1 is because it approaches the x-axis extremely fast. I had to zoom in really, really far just to see the separation when we were around, say, -5.5 standard deviations. So that's what makes this all work out finally in the very end. But that's our curve. Let's take a screenshot of it and place it down on the notes. Example 1 is not something that you would be asked to do in class for quizzes or exams. Really, for us, it's just a chance to catch our breath, take a look at what these normal distributions look like before we start doing calculations with them. So here's our first one. Any questions about it so far, folks? Okay, let's make some weird connections about this next. Actually, I want to expand it just a little bit more. The first connection that I would see here is through this quantity. This was plotted where the parameter was set to 0 for us. Now, that's a location parameter in the sense that mu measures the center. We have multiple competing measurements for the center, but we're using the average here for this distribution. If it measures the center, then your peak right up here should be below 0 on the horizontal axis. That's exactly what we see, and that's what mu is doing. If you change mu, you're changing the center, and you're moving this whole curve either to the left or to the right, depending on that value of mu. Any questions about that so far? Okay. Another thing that happened here, which is really hard to see on this plot, we need multiple plots to find the effect, is about what sigma is doing. I guess we can highlight it here. I thought I'd change the sigma on that value, but apparently we didn't, so we'll come back to this. But sigma is not a location parameter. What sigma is telling us how spread out the actual data is. So this is variability. We'll say here, this measures the spread. Or you could say variability. I like spread because it's more visual. We're talking about spreading things out. The larger the value of sigma, the more the area under this curve is going to be spread out. The smaller sigma is, the less spread out it's going to turn into. So that's what we have so far. Now let's start changing some of these parameter values just to see what happens. But first, let's maybe put one additional thing on the notes. We're looking at population characteristic, these parameter values, but don't forget that mu is approximately equal to the statistic x bar, and that sigma is approximately equal to its statistic, which is the standard deviation S. These are easy to forget since we just haven't been talking about those things as much. But now we're getting closer to statistical inference, they'll start coming back a whole lot more. Really, a lot of chapter 1 is going to come back as well. Well, that's our first graph. All we're going to do is start practicing with more. Yeah, go ahead.
Well, we're doing like exam.
Mhm.
Do you care which one we use to exam for mu and standard deviation? If we use the mu or the x bar or the sigma or the s?
Actually, it does matter, yes. So for the purposes of exams, you have to be very careful of which ones we're actually going to use. But I think it won't be as bad as it sounds, because once we're dealing with these characteristics, values, population characteristics, the question is really going to be centered about them. They'll say, find a confidence interval for mu, the population mean of whatever it is, heights or something like that. So it becomes a little bit less of an issue, but we're starting to get into the work where we will start paying attention to these versus these, and we'll have to separate them in our mind and our work as well. Does that answer your question about that?
Yeah.
Yep, you betcha. And just to add a little bit additional, let's say, again, these are the population characteristics, or you could call them parameters. And these ones are the statistics. Again, it's kind of a rehash of those kinds of things we've looked at in chapter 1. But that's the good thing about this section is if you've seen it once, it's not too bad to absorb it again. So these will be things that become very familiar at the end of the semester. Other questions so far, folks? Okay, well, let's turn to our second example, or the second part of the same example, really. What we're going to do now is change the value of mu. We know that it measures the center, so if we set mu to -2, any predictions on what happens to the curve? Should it go right or should it go left? I agree, it ought to go left. Let's see if it works out. So back to Desmos. We can make that a little bit smaller now. We're putting in the value of -2 for mu. I have my mu set to 0. Again, this is a bit regrettable. After I said that earlier, this S is supposed to be the sigma value, but I couldn't actually put in Greek on this thing. So imagine this as a sigma, not as an S. But we're moving this to the value of -2. And so what happens is, let's go -1, -2. The whole thing just adjusts, and that's our new graph. It just centers at that new location. So really, that's the whole effect of what happens when we change the value of that population characteristic mu. It's just moving where the central peak is, where all the data is accumulating. Let's put this in as our next screenshot. So we'll place it right here. Again, the purpose of these screenshots are really for us to determine what's happening if we change one of the population characteristics. So when we change this to -2, we just have a new main peak right here at -2. Sigma was 1, so the spread of these data is just the same. That's why the shape here looks like the same shape as the one down below. I have this one zoomed in just a little bit more. Actually, that looks kind of jarring. Let's see if we can kind of fix that. Not easily. Let's fix this as well. And so that's the effect of just moving that one parameter. Well, the exciting one is now sigma. So let's start moving sigma around and see what happens when we change that value. So at sigma equals 1, we're going to change it to 10. We're going to set mu back to 0 since we know what happens when we move that value around. It just changes where the main peak is. But setting it to 10, let's think about this for a moment and see if we can predict what should happen. Recall, sigma is telling us how spread out the data is. Here it's spread out by a factor of 1 for the population standard deviation. We put in a value of 10. Would you say the spread is increased or decreased? Is it more spread out or less spread out? I agree. The higher the value of sigma right here, the more the variability, the more the spread. So take a look at this picture. Area under this curve is still exactly 1, but we are spreading out the area by a massive quantity. The whole curve should flatten on us if we do that. Let's take a look at Desmos and see just what happens. So I'm going to set mu back to 0. Here it is at a value 0. We want to make S grow. So at 2, it flattened a little bit. At 3, a little bit more. And the larger this gets, the closer to 10, the more it looks like a straight line. That's kind of bonkers in a certain way, because when we go to plot this, we are not going to plot that straight line. We're in fact going to plot a line that looks like that. That's really, really weird about the normal distribution. But it's all a matter of perspective though. This is just the wrong graph because we're zoomed in too far this time. Now we need to zoom out, and here's how we'll do it. When we set the standard deviation of the population to 10, this is not even going left 1 standard deviation, it's only at -2. We should be going to the left by, say, 40, and to the right by about 40. and we'll get a much better picture. Let's see if that can happen for us in an easy way. So let's go for the x-axis, -40. For the y-axis, +40. And we can do the same trick with what's going on right here. We now need to zoom in vertically. We can drop maybe a -1 here, go up to a +1. Not a whole lot of difference on this one, but noticing it's at 0.5, we should maybe be zooming into 0.1 this time. So here's 0.1 on that location, -0.1 on the lower end. It finally gives us back to the same exact shape. And this is what's kind of weird about the normal distribution. It's the reason why in section 3.5, when you go to draw a normal curve, we're always trying to draw the same shape. And it doesn't matter what your mean is or your standard deviation. It's always going to look essentially like this each and every time. So let's drop this in. And you know what? Let's change this a little bit. Another thing that we did when we plotted these, and we're going to continue to do so in section 6.5, is we never even considered the vertical axis. It's really just noise for us. It's a distraction that's not needed. So in our plot, let's just take it away. Okay, y-axis is gone. This is more like what you would really plot on a real homework problem. So we'll go from -30 to +30. Even with a standard deviation 10 times as big as in part B, our picture is still, well, it's the same thing. It just has different values on the horizontal axis and the vertical axis, but we also suppress the vertical axis. We don't need it to calculate probabilities or find the areas under the curve. So the difference was, with a spread of 1, everything's pretty centralized to the main peak. But with the spread of 10, it spreads out massively. So we also zoomed out a whole bunch on the horizontal axis as well. Let's maybe try one last one to finish this off. We're going to change it to a 0.1 this time. So here we have very, very high variability. We're changing it to low variability. There's actual values that sigma cannot equal. You cannot put 0 here. If you did put 0 here, you're saying everybody takes on the value 0. And that would be a sad dystopian future where everybody's exactly the same. But real data has variability, and so do these values. It never hits 0 for real data. It can't be negative. The value of 0.1 is actually really, really small. Let's show what would happen to this graph. I need to change the step size to 0.1 so we can actually put that value in. So we're going from 10. Now, as I make this smaller, what would you all say happens to the peak? Should it go up or should it go down? Really kind of hard to visualize, right? But think of it in these terms. The smaller S is, the less spread out. You'll still have a total area of 1 unit. So if 1 unit is less spread out, this peak right here starts to skyrocket. Let's double check if that reasoning is correct. So I'm going to take this, make it smaller and smaller and smaller. And the smaller we make it, the more the graph just looks like it's broken. Here it is at 0.1. The graph doesn't even plot correctly like at this stage because the pixels are too big to show the fine detail. But like you're expecting, we just have to correct this graph. If the standard deviation is at 0.1, at 40, that's 400 standard deviations to the left. That's way, way too far. We just simply need to zoom in. So we'll go back here. Let's say go from -0.4 to +0.4. On the y-axis direction, we now have a strange plot, but we can fix that. Let's make this go to, how about a 0.5? That didn't work. Maybe a 1, 2, 3, 4. Right around 5s and 6s, it's starting to work. But that's because the spread is extremely small. All of your data is piling up in this one location. So this is the largest value on the y-axis we put in on any of the plots. We can maybe just drag it up, go like that. This one has a higher peak, but we could change the zoom if we wanted to and make this one graph look exactly like all of the rest. So I'll leave this one just as is with a slightly different shape. But all these shapes are correct whenever you go to plot a normal curve. Kind of a wild experience, but here they are. When I try to plot them, I try to make them look like this. Then I just put the right values on the horizontal axis that makes the shape correct. We suppress the vertical axis, so we're not even worried about any of that information in any of these problems. But that's what it all looks like. Next thing we would like to try to do is calculate some values on these and see just how it works. Any questions at all first before we try? Okay, well, we have a plot right here. Let's make this one our warm-up exercise before we try out example 2. Let's call this warm-up is a fine thing to call it. Let's call this warm-up. We'll think of this as an x-axis, like we mentioned before, and let's calculate the probability that x is bigger than 0.1234. Just a bizarre made-up problem. First thing I'd want to do for solving this problem is visualize it. So my step 1 would be to draw the graph right here. But now we need more information about that graph. Let's recall that this had mu set to 0 and sigma set to 0.1. We absolutely need to know that information to get through this problem. So here it is. Next thing we do is we go to the x value in question, 0.1234. We're going to attempt to plot it. It's really hard on this one, but that's okay. Our plot is just to organize the information so that we know what goes into the calculator and in what order it should go into the calculator. So 0.1234 is maybe about here, right around that location. We'll put it in a vertical line segment until we hit the normal curve and then just stop there. Now we have to make a big assessment. What we have to decide is, do we want the area to the left or do we want the area to the right? In other words, which side should we shade? Anyone see what the issue or what the resolution should be to this? To the right? I agree, absolutely. We'll shade to the right only because of that inequality symbol right here. We're saying x is to the right of 0.1234. That means your x is anywhere in this range, going off to positive infinity. Remember, the curve never actually stops. That's what's weird about the normal curve. So let's put here, just as a quick note, x is to the right of 0.1234. That means we'll shade to the right of that value. So we can take off these question marks, and here's the shading. Kind of low effort, but just enough so that we know which region we need. Now, the reminder of why are we shading is because whatever this probability comes out as, it's the area under the normal curve to the right of 0.1234. So the answer is this area. If we can find that area, then we're all set. And the trouble also is there is no way the empirical rule works on this. The empirical rule wanted exactly a value here, 1 standard deviation away, or here, 2 deviations, and so on. But we have a weird calculation. Nonetheless, we can still make this happen. So here's how I would organize this on the graph right before going into the calculator. I'm going to call this position 1.234. And then in purple, this is going to be the first entry that we'll be putting in. Sorry, question first?
Is that 0?
Oh, yes, absolutely. Thanks for mentioning that. 0.1234 with a 0 in front of that. So 0.1234. Thanks again for spotting that. That was going to look really weird in the calculator. Then my notes in purple are what's going in the calculator when we go to solve this. So I'll point to this one. I'm going to call this 1. I'm going to call it lower. That'll make more sense when we put it in the calculator. It's my lower bound is the only reason I'm calling it lower. That there's no x's to the left of that. That's the lowest one we'll put in. And now there's no upper bound. X is to the right and it's never actually going to stop. So on this graph, I'll put 2 upper 10 to the power 99. What's the strategy here? My strategy is I'm trying to put in the largest number you can put in a TI-84. That's the largest number. And the reason I'm doing that is when you say X is bigger than 0.1234, it's not stopping. So I'm attempting to put something that's essentially an infinity for this type of problem. Largest positive number you could ever throw in. So that's going to be the second thing to enter in. Then we take a look at the population characteristics, the parameter values. This will be input number 3. And this one will be input number 4. And we will call this problem a normal CDF problem. So now this is the organization. We're about ready to put it in the TI-84. Anyone have any questions so far before we pull out that calculator? Okay, so inside the calculator, here is our new sequence of steps to get through this process. Because this is so very different, I'm going to show it just as a normal calculator like we're used to seeing. But I'm also going to take screenshots and post the steps down right here. That way, if you have any trouble getting through them in WebDesign, you can also turn to the notes to just see a step-by-step guide. So right here, I'll call this step 1. And in step 1, well, first thing we have to do is turn on the calculator, but we need to hit these 2 buttons. We hit the second key. Let me pick a color that shows up maybe a little bit cleaner. How about lime? I think that'll show. Yeah, that's much better. We hit the second key, and then the key which I'll refer to as bars. So second bars is often what I'll say quite a lot. So that's essentially our step 1. It's going to pull up a new menu. Give me a moment to put this on the document, and we'll put in our step 2. Okay, so I actually have to hit those buttons. Let me hit them right here. So here's second and bars, and here's the window that we're pulling up. These are now probability functions relative to this kind of probability model. We are dealing with a normal CDF problem, so we go to option 2, normal CDF. Now, there's often a question about this. What does CDF stand for? It stands for cumulative distribution function. You don't have to memorize that, but if you take more statistics, you will take more probability, and then that will be something that's covered. For us, we just have to think of that's the right thing to take. When it says cumulative distribution function, the thing we're accumulating is this area. So that's why it's called that certain way. This is our step 2. We have to hit that button. So I'll just say, choose that option number 2. So back to our guide, choose option 2. There it is. We're going to choose option 2. And that takes us to the fun step, step 3, fill in the relevant information. So back to this. I'll hit enter right here on option 2. And here's the information that we have to fill in. In your calculator, it probably looks exactly like this. If it's used, it might have information already put in, but no worries either way. What I would do right at this step is return to the graph. This is the major reason we're spending time on these kinds of graphs. It organizes everything that goes into the calculator. And oftentimes when you're solving these kinds of problems, if you're not sure what goes in what location in all these options, the first thing I would probably say is, well, what does it look like on your graph? On our graph, we'll read it left to right. We'll stop right here. Here's entry number 1 for lower, matching where it says lower here. We're just going to punch in 0.1234. So there it is for our lower value. Now, sometimes we put in a number like 5 for the upper, but that's only if X was no larger than 5. In this problem, X exceeds 0.1234, never stopping. That's the only reason we put upper 10 to the power 99. So in the calculator, here's what it looks like. Hit enter, type in your 10. Now to put in a power, it's this button, the little up arrow. So 10 to the power of 99. It should look just like that inside your calculator. Any questions at this moment so far, folks? Okay, so often the lower value, the upper value, that's the trickiest thing about this entire process. And the good thing is right after that, the calculator can print Greek. I couldn't do it in Desmos, but it's asking for your new value. If you don't supply it, it's going to use it as a 0. We have to change these on every single new problem because we expect mu and sigma to change on every single problem. We're just lucky here it's 0, so I'll leave it as a 0. Let's type it in so we feel like we did something. This one has to change. It must be 0.1. So your calculator should look like this before hitting your enter keys. This fills out step 4, so let's paste it right down here. Or if that's step 3, I'm confused on the steps. Here's where we're going to end up at, step 4. Let's call this success, because at this stage you've done it. You just have to grab that actual probability. So back to the calculator, hit enter. Right here where it says paste, it'll look like this on the TID4 Plus. This is a good time to mention, if you spent a little bit extra money on your calculator, maybe you have a TID4 CE edition, maybe it has a charging cable, a nice LCD display, it'll look a little bit different in your calculator, but all the information is essentially the same. So hit enter one more time, and this is the probability that we were trying to find, 0.1086. I want to take a screenshot of this. Let me try a better screenshot. There we go. Since when we say success, I mean, we still have to answer the question, right? And here's what the answer to the question is going to look like. The probability that X was bigger than 0.1234 is now equal to this number here. Let's say we round to 4 decimal places, which is pretty common, 0.1086. So that's the probability that X exceeds 0.1234 in this situation. Well, any questions, folks, on the conclusion here? Okay, so that's how we're working with the normal distribution now. The empirical rule was still a handy guide. It helps us think about what's really happening when we put together a mu and sigma value. But really from this class forward, every time a normal curve comes up, it's going to be in this way that we calculate it. We'll hit second bars, we'll normal CDF, and put in the relevant information. But now the tough thing about this topic, you might have noticed it's multiple days on the schedule for the syllabus. This is just one scenario. We could have said X is less than a value, or X is between values, or we can even do a percentile style question, and we're not even using normal CDF in that kind of problem. So we'll probably spend some time on these notes just getting a handle on this, because we'll do a lot of normal distribution computations going forward. But any questions at all, folks, on running through the process? Okay, well, let's try this out maybe one more time for a slightly different scenario. I mentioned sometimes things feel backwards when you do this whole process. Sometimes your question is a percentile style question. You're grabbing a value on the horizontal axis, just like say on exams and quizzes. Or maybe it's a probability question and you're grabbing the percentages. Let's do a second warm-up question where it goes this way. We want to do a percentile style question. So the question could be, what is the probability? Let me put an X here just so X has meaning. X is a value on the horizontal axis. We want the probability that X less than K, now that looks weird, we have an unknown value, equals 0.307. So we want to solve this for K. Let's actually say that. Solve for K. This is a true mathematical equation, one equation with one unknown, but this one is pretty bizarre. To actually solve this equation, here's what we need to do. It says X less K, so once again, we need to think in these terms. It's all about the area under the curve with our new model. So we'll say the area under the curve, the less than sign is telling us to the left. Of our K value we're trying to find is 0.307. So the first thing we have to worry about is the inequality sign and the direction telling us area to the left. Now I'm going to put a couple things down on this chart, but I'm going to erase them immediately. So if you have pen today, maybe don't copy them just yet. But what I want to put down is right here, K could not possibly be that value because, well, that splits the total area in half. There's area 1 to the left, or excuse me, there's area 0.5 to the left, area 0.5 to the right to get total area 1. So K can't be here. I want the total area to the left of K to be 0.307. It's too large at 0.5. So now here's the question for the class. The area is too large to the left of K. Should K move to the right or should it move to the left? You're saying left? Any others for left? Right or left? Looks like going left. Gotcha. Sorry, I have a perspective issue. I think I agree with folks. Let's move it to the right to just get a feel for this. If we did move it to the right and say, place it over here, well, I would guess that about 80% or 0.8 of the areas to the left, these are just guesses, and about 0.2 of the areas to the right, if it was right over there. So we put it way, way too far. If we're trying to get K solved exactly, we want 0.307 to the left of K, should probably be more around here, somewhere on the left end of 0. So let's place our K value, our unknown to solve, maybe about here. Not trying to place it perfectly, I'm just trying to organize the information on the graph so that we all know what actually goes in the calculator. So here's K. We want the area to the left of K to be that quantity, 0.307. So next thing I would do is shade here, 0.307 with the arrow goes into that location. This is an area, so it's a good time to remind ourselves. And that's entry number 1 in your calculator. The calculator wants your area right away. It also wants mu. In this problem, mu is 0. It'll want sigma. And sigma was 10 in this problem, where I copied the screenshot. So this will be entry 2. This will be entry 3. But here's the thing that's kind of wild about this problem. This is not a normal CDF process. So we'll not use this normal CDF function. It's inverted. It's a complete backwards type process. So if you ever see this, where you want to solve for K, use INV, that stands for inverse norm. So we need to use the inverse norm option for this particular problem. I'll show it once in the calculator. I don't have time to actually show the step-by-step guide, but I will update the notes so it does show that guide. But since we're short on time, let's just go through it once and just see what it looks like. Let me know if you're getting different values out. First thing I'll do is turn it on. Our mantra is hit second bars. Now, normal CDF does absolutely nothing for us. Normal PDF does nothing for us at all. That's just to graph the curve. That just tells us what the height of every point is. But inverse norm, that's the one that's going to give us the solution to K. It solves for K immediately. Hit enter on this option. And the first thing it's asking is, what is your area? I'm going to make a big deal out of this every time we do it, but we're kind of shy on time at the moment. But the big deal is we're always talking about area to the left, regardless of what's happening in the question. Even if this was a greater than sign, I would still have to find this area to the left and plug it in right here. So 0.307 goes into that location, then change our parameter values. Mu has to be 0, sigma has to be 10, and we should get this value of K right here. It's also going to confirm or deny how accurate our guess was. looks like I was guessing about -11, but I'm not sure if it should be to the right, around maybe -8, or to the left around -13. Hit enter a bunch of times on this thing, and it says, well, it should have been at -5 altogether. So I was quite a bit off on my graph, but that's okay. Your graph is just to organize the information. So even if it's misplaced, that's okay. So K is -5.04. And so that's the process of solving for K if the probability is known, but the K value is missing on the horizontal axis. Think of both these questions as really kind of warm-up questions. The actual problems in WebAssign that we're about to solve are the ones down below. But since this is such a hugely reliant problem on the calculator, it's a good idea to just practice with these first. When we come back on Wednesday's class, we'll return with these notes and finish off the next problems. Well, any questions, folks, before we call tonight? Okay, well, have a great night, folks, and we'll see you all in Wednesday's class. Any questions?
Yeah, when I do the second bars thing.
Oh, weird.
The second click, it says this.
Oh, geez, let me see if I can help you with this. I'll just go to fit first. Let's go second bars. And was it the problem on the inverse norm or the one above?
The first one.
Okay, let's take a look at this one. So this will be normal CDF. Oh, your calculator is a little bit different from mine. It's kind of unfortunate that even though it says TIU4, this one's a plus, this one's a silver edition. Your calculator is just a little bit older, but here's how it's going to go. The numbers I'm putting here are always going to be in the right order for your calculator. So it'll be a 0.1234. And you have to literally type in a comma. That's kind of weird. Sorry about that. Go to 2 right here. 10 power 99. Then comma again. Then go to number 3, which is a 0, comma number 4, which is a 0.1. And then you have to close the parenthesis to make it look like that. Then if you enter on that, you should be getting the 0.1086.
Yeah.
Is it working out?
Yeah.
Awesome.
Do I do the same thing for the inverse norm if it does that?
Yeah, it would be the same kind of thing. You'll have to give it the area first, a comma, then this one, and then that one.
Okay.
And I just want to let you know that I also have this. Let me try this again. File, open. I have this calculator, which is extremely similar to yours. So I could go second bars, normal CDF or inverse norm. It's going to always look exactly like yours. So I could show this in class as well if you like. Just let me know if the problems ever cause you trouble. I could run through it on this, and that's going to look pretty much identical to your screen.